Welcome to podcast number 6 about LeChatelier's principle. Again, this is one of those topics where I find that students do sometimes struggle figuring out LeChatelier's principle. This will come up in about 3 or 4 chapters itself, so don't slack on learning LeChatelier's principle. There's always a whole bunch of questions on your next exam about LeChatelier's principle. They're easy multiple choice questions, so expect them on the final as well. Right? LeChatelier's principle should not be that difficult, but you just kind of have to use your inside reasoning as opposed to being able to do a whole bunch of math to be able to figure these out. So, Henri LeChatelier lived at a time when people apparently still wore glasses that didn't have the advancement of the thing that comes and hooks over your ear, had to pinch you on the nose, which seems really uncomfortable. But he came up with the fact that if a system at equilibria is disturbed by changing something, then if the system can, it's going to find a way to shift to restore equilibria. All right, so what that's saying is, like, if you make something that was at equilibria and you throw it out of whack, it's going to do everything that it can to find a way back to equilibria itself. Let's start by adding or removing a gas. All right, you can read the top couple of bullet points there. Like, if a chemical equilibrium is disturbed by adding a gas, right, then we're going to shift in the direction that consumes the added species. Okay, a lot of people like to either you understand what is stated there and you'll have no problem doing this, or a lot of people like to write the teeter-totter method of this. So let's say that I have A is going to be in equilibria with some gas B. All right, so we've got my equilibria there. Okay, let's say that they are on a teeter-totter. When they are nice and perfectly balanced, they are at equilibria. Okay, I'm going to add a gas. We're going to add some A. When I add A, okay, well, that side of it is going to get a little bit fatter than the B side was. All right, well, the only way in order for us to reestablish equilibria is to shift to consume A. All right, and another way of saying this, we're going to shift to the right, which is to make more B. And if we shift in, we can go back to our equilibria like so. So if we shift and we go, okay, I am, like, on the heavier side of my teeter-totter, right? We've got to figure out a way for that side of the teeter-totter to get a little bit lighter and the other side to get a little bit heavier to equal out. All right, so that's what happens when we add a gas or reactant. The opposite of that's going to happen if we remove something. Right? Just again, think about sitting on a teeter-totter, like you and a friend are sitting on a teeter-totter. All right, if, you know what, you were sitting on a teeter-totter and you, say, cut off your legs, right? Now you're going to weigh less. So you have removed some of you by cutting off your legs. Don't do this. It's a thought experiment. Well, we're going to shift in a direction to add some mass back to you, because you're going to hop up into the air. If you were at equilibria with your friend and you cut off your legs, you're going to go up and your friend's going to go down. Well, to go back to equilibria, we got to figure out a way to, have your friend, maybe take off all their jewelry and give it to you so that you're weighed back down again. You got to figure out a way to come back to equilibria. That's what's happening here. So another one, right, if you haven't gotten it yet, we can say that, right, again, we're going back to our dinitrogen tetroxide in equilibria with our nitrogen dioxide. If we add more into O4, right, that side's going to go down on our teeter-totter. We've got to get rid of into O4. We're going to shift to make in O2. We're going to shift from left to right. As we do that, If we add NO2, then the opposite would be, right, we're going to shift away from what we add. When we remove, right, we're going to shift towards what we removed. So when you add, you're going to shift away. When you remove, we're going to shift towards what we removed. And if you can just memorize this, then you can get some of the LeChatelier's principle problems correct. A lot of them have to do with whether we add or remove something. Now we can get a little bit more complicated in that, and we are going to. Okay, still not that difficult, but albeit a little bit more in depth, is what happens if we change the volume, right, of our system. So say you got like a balloon, it's filled with gas and it's at equilibrium, but we decide to change the volume of it somehow. So we've got our N2O4 and our NO2 again. All right, if we reduce the volume, remember that when we reduce the volume, right, volume and pressure are inversely related to each other. So if I take a balloon and I squeeze the volume in, right, if I reduce that volume, then the pressure has to go up. So the pressure is going to be larger. All right, well, how could we counteract that? Well, remember that also, right, pressure and number of moles are directly related. Okay, so if we shifted, right, this reaction, say from our NO2 to the N2O4, notice that for every 2 moles that we had, we're now making 1 mole. So the number of moles are going to decrease, which would mean that our pressure would decrease. All right, so when we reduce the volume, we increased the pressure. But if we shift away from NO2, we're going to alleviate some of that increase of the pressure by decreasing it back down some. And so the system is going to do that. So here we're just reiterating what we said, right? When our system is compressed, right, when we took our volume and we squeezed it in, our pressure increases, right? And so what we want to do is we're going to shift in the direction that will decrease the total number of moles of our gas. Notice that it is only the total number of moles of gas. It's not the total number of moles. If there's a solid or a liquid in there, that doesn't affect the pressure. And so we only care about the total number of moles of gas that is in there. All right, if we expand our balloon, right, then the pressure decreases. We're going to shift so that we're going to increase the total number of moles of gas. And then lastly, right, if the total number of moles of gas are both the same on our reactant and product side, right, by our ideal gas law, right, it's ideal, and so they behave the same way. By shifting it, we're not going to do anything. And so really, a pressure change isn't going to be able to be counteracted by LeChatelier's principle in that case. The last factor that we're going to focus on when it comes to LeChatelier's principle are changes in temperature. Right, an increase in temperature is going to favor the endothermic reaction. So we have to remember what is endothermic and what is exothermic. Remember that an endothermic reaction has a positive delta H. And so as the top reaction there is written, N2O4 in equilibrium with NO2, if we increase the temperature, we are going to drive that reaction to the right. All right, now notice though, on the other reaction down there, N2 plus 3 hydrogens in an equilibrium with our ammonia. That is an exothermic reaction. But remember that when we have our exothermic and endothermic reactions, if I were to reverse that reaction, right, and I wrote it the other way, and I had 2 ammonias in equilibrium with nitrogen and our hydrogens, then the delta H for that would be positive 92.2 kilojoules. That is endothermic. And so what we're saying there is that this would then favor us going and producing more nitrogen and hydrogen. All right, the other thing to get is the only factor of LeChatelier's that affects K or changes our equilibrium constant is temperature. All the other ones will shift which direction things are kind of going, but the overall equilibrium constant won't change. But temperature does change it. That's the only one that will. Well, here we have a sample problem dealing with LeChatelier's principle. And for the most part, I'm going to have you guys go through each one of these and see if you understand them. They're written out really well for you. We'll go through the first one here just to make sure that we understand what I'm writing out. If I removed oxygen, how does that affect our ammonia? Well, remember that if we remove something, right, by LeChatelier's principle, we have to then try and drive a way to replace that. And so we're going to replace the oxygen by driving our reaction back to the reactant side. Well, if we're making more oxygen by going to the reactant side, we're also making more ammonia, which would lead to, right, that increase in the amount of ammonia. We're getting more of that because we're going that direction. All right, same thing, we've got one where we're going to add nitrogen and see how that affects it. And we got some other ones as we go through. Let's see what's on our next slide. Well, let's talk for a second here about adding water. Right? Notice that if we add water, water is a liquid in this case. All right, if you add a liquid or a solid, then it's not going to affect our equilibria. Same thing as if you add something that is not in the actual equation. All right, so let's say that I added some argon gas to this. That's not going to affect anything in the equation whatsoever. It's not going to drive our reaction one way or the other, so it's not going to affect anything. So just keep that in mind when we're working these, right? It only has to be one of the gases, right? It can't be a liquid or a solid, and it has to be actually in our equation to affect it. All right, make sure that you understand expanding, what happens, right, to expanding our container. All right, our last one is increasing the temperature. And so increasing the temperature is an exothermic, and this in an exothermic reaction is going to drive our reaction back towards our reactants. All right, and one of our reactants was ammonia. All right, so that one's pretty straightforward, but it says, all right, in F, which of these increases the value of K and which will decrease it? All right, now recall, only temperature affects K. All right, so only E has a possibility of changing it. And now what I want to do is I want to think about this, right? K is equal to products divided by reactants. All right, and I could write out everything that's there, but let's just say, all right, products divided by reactants. What's happening here? Right, this caused the reverse reaction. And so our reaction is going towards making more reactants. So in this case, the reactant side increases, the product side is decreasing. All right, so the number in the numerator is going down, the number in the denominator is going up. Thus, our K has to be going down. All right, so that ends LeChatelier's principle. Again, I would bank on there being quite a few points and quite a few questions about LeChatelier's principle on your next exam. And then it's going to come up in other chapters as well, and probably on the final as well. So get used to the Ch13.6 principle. Get those ones down. Our last podcast in this chapter is going to deal with something that we call the Van't Hoff equation. Hopefully it's something that's going to look really similar to us.